Okay, we've looked at structures of compounds and seen the implication that they have on the properties of molecules. We've also looked at just the simple kind of bonding that occurs between molecules, ionic or covalent, and how that impacts properties. There's another fairly large factor that impacts what properties compounds have, and those things are called intermolecular forces. We're going to distinguish between inter and intramolecular forces, and then we'll look specifically at three types of intermolecular forces. Okay, so intra versus inter. The two types of bonding that we've looked at so far, ionic and covalent, would be known as intramolecular bonding. In other words, bonding that occurs within a molecule. All these bonds that I've indicated here, sorry, it looks like double bonds, but this bond and this bond and this bond and this one are all examples of intramolecular bonding. So in methane, I've got bonds that are holding the carbon and all those hydrogens together. That's intramolecular bonding. These particular ones are sharing, so that would be a covalent bond. Now, there's another kind of bond, but I guess we would call it a force, that exists between molecules. So here's a molecule of methane, here's another molecule of methane, and the bonding, not the bonding, but the forces that are attracting between those two molecules are called intermolecular forces. So forces between molecules are called intermolecular forces. And it turns out that there's three types of those attractions. So there's not only attractions or bonds between atoms in a molecule, but there can also be attractions between one molecule and a neighboring one. Here's a molecule of water, here's another molecule of water. Are there things that sort of attract or try and keep those things together? If there are, then that has implications on the properties of that molecule. So the first one, or the three types of intermolecular forces that we'll look at, one's called London dispersion forces, another one's called dipole-dipole, and the final one is called hydrogen bonding. Some molecules might only have one type of force that connects them or keeps them together. Other molecules might have three types, might have all three of those. So it depends on the type of molecule. So we want to determine what constitutes LD forces or dipole-dipole forces or hydrogen bonding. So first off, London dispersion forces. These forces exist between all molecules, all of them. So it doesn't matter if they have the other two kind of forces or not. All molecules have London dispersion forces. And there are attractions that exist between the electrons of one atom and the protons. Remember, electrons are negatively charged, protons are positively charged. Electrons of one atom and the protons of a neighboring atom, or a neighboring molecule is probably the better way to say that. Molecule. So here I have one molecule, and I won't draw the whole thing. And here's another molecule over here. So in this molecule, of course, I would have protons in the middle, and I'd have electrons somewhere around the outside. Okay? In the other molecule, again, protons in the middle, electrons somewhere on the outside. So the attractions, or London dispersion forces, are attractions that happen between the electrons of this molecule and the protons of a neighboring molecule. Indeed, there's probably attraction between these protons and the electrons of that molecule too. So they're weak attractions. However, you can see it in one property, boiling point of noble gases. Right here are the noble gases, helium, neon, etc. Helium, according to the periodic table, has 2 electrons. And notice its boiling point, negative 269. So really, really cold. Now, a little bit warmer is neon, and how many? It's got 10 electrons. Argon has got 18. Notice I'm picking this number here. Krypton's got 36. But the only difference between these molecules is the size of the molecule and the number of protons, number of electrons. So 36, 54, 86. So as the number of electrons increases, the boiling point also increases. Notice that here we're not quite at 0, but negative 62 Celsius, that's a whole lot warmer. Doesn't sound warm, but it's a whole lot warmer than negative 269 degrees Celsius. So those are London dispersion forces. Here's just a quick example. Methane has 10 electrons. I just counted them up down here. Carbon tetrachloride's got 74. Carbon tetraiodide has got 218. Again, compare the boiling points. These ones I did in Kelvin just so they were easier to compare. And again, take a look. As you increase the number of electrons, the boiling point also increases. I don't know if there's an exact direct relationship. I'm a math guy, so I'm looking for, if I double the electrons, does that double the boiling point? It doesn't look as though it does that here, but I see a general trend. Increase the number of electrons, increase the boiling point. Those are London dispersion forces. The second type of force that we'll look at is something called dipole-dipole forces. And these are forces that exist only in polar molecules. So the molecule has to be polar. If you forget what that is, go back in your notes and take a look. They're similar to ionic bonds, but they're not as strong as ionic bonds. Similar because they are an attraction between a plus and a minus end. For example, when I take a look at this molecule, hydrogen chloride, I see the electrons here, and I see that they're sharing these two electrons. But since chlorine has quite a bit higher electronegativity than hydrogen, the electrons are way closer to the chlorine than the hydrogen. And what happens because of that is because, as a result of that, since there's more electrons on the chlorine side, this would be a partially negative end of the molecule. This side here then would be partially positive. So, if I have a molecule that is sort of polar like this, if I have another molecule that's similar to it, close by, it would arrange itself this way. And the dipole-dipole forces are those attractions that happen between this partially negative side and the partially positive side. Partial positive, partial negative. So there's attraction between plus and minus. And those attractions there are known as dipole-dipole forces. And what they do is they keep those molecules together longer than if there were no dipole-dipole forces. Here's another example beside here is water. So with water, I'll just draw how it would be. Here's a bunch of electrons over here, so this side of the molecule would probably be partially negative. This side might be partially positive. So in this molecule, this side would be partially negative, this side would be partially positive. So here, partial positive, partial negative attractions there. Okay, and those are dipole-dipole forces. Here's three more examples. This is methyl chloride. Notice the chlorine's on this side. Notice also that the molecule is asymmetrical, like it's not perfectly symmetrical. There's this big green kind of blob way over to the right. It's chlorine. This side is probably going to be partially negative, forcing the other part of it to be partial positive. Things line up again. Again, sulfur dioxide, it's an asymmetrical molecule. It's not perfectly symmetrical, so there's going to be some kind of partial positive and a partial negative side to this. It'll be polar molecule. There'll be dipole forces. Lastly, chlorine, fluoride. These guys are pretty close. Chlorine, I think, for electronegativity is 3.5, and fluorine is top dog at 4. But still, there would be unequal sharing of these middle electrons. and so there'd be a slightly negative charge on this side, slightly positive charge on this side, dipole-dipole forces. The last type of intermolecular forces that we'll look at are something called hydrogen bonding. These are fairly easy to point out because they only happen if you have a nitrogen, an oxygen, or a fluorine in your molecule. And the nitrogen, oxygen, fluorine must be bonded to a hydrogen. So hydrogen bonded directly to nitrogen, oxygen, or fluorine. Water is a great example. Right here I've got an oxygen bonded directly to the hydrogen. If I see that, automatically hydrogen bonding. Now, what is hydrogen bonding? Well, what happens is because oxygen is so highly electronegative, these electrons are spending most of their time by the oxygen, making hydrogen almost like a positive charge. It might be a partial positive, but it's almost a positive charge because oxygen is pulling those electrons so much. If it's positive, then it can be attracted to anything negative. And in an oxygen molecule, it's got two non-bonding pairs of electrons. So hydrogen bonding is the attraction between those non-bonding pairs of electrons and the hydrogen of a neighboring atom. So hydrogen bonds are those attractions that exist between the hydrogen of one molecule and the non-bonding electrons of a neighboring molecule, specifically nitrogen, oxygen, or fluorine. Here's some examples. For fluorine, really the only example that exists is hydrogen fluoride. There might be some other ones, but that's the only one that you'll probably see in this class. But hydrogen fluoride would be an example. For oxygen, there's tons of examples. We saw water already. Alcohols are great examples. There's an O bonded to an H. There would be hydrogen bonding there. Notice this molecule would also be asymmetrical, so there would also be dipole-dipole forces there. Organic acids like ethanoic acid or benzoic acid, other examples where there'd be an oxygen bonded directly to a hydrogen. With nitrogen, perhaps the only example, well, there might be lots of others, but ammonia would be one example. Amines or amides would be some organic compounds that would exhibit hydrogen bonding. Okay, so we've looked at three types of intermolecular forces, forces that hold molecules together. LD forces, dipole-dipole, and hydrogen bonding.